Why should you implement storylines into your high school chemistry classroom? In the past 20 years of high school chemistry teaching, I've done a lot of labs. They were good labs. I approved upon them. I enjoyed them. But after all this time, I was ready for a change. Plus, with the new next generation science standards coming into play, I wanted my labs to be more connected, to flow from one lesson into another. And so this year, I tried to implement the first of many storylines that are out there called Why Do Some Things Get Colder or Hotter When They React? In this video, I will summarize this storyline in its entirety. As you can see, there are a total of 12 lessons, which took me from September all the way to spring break, but spending only one lesson a week on this storyline. I wanted to take baby steps. In the very first lesson, students got a chance to observe themselves by mixing a couple of chemicals, an endothermic reaction. Because as you can see, upon lifting the beaker, it was stuck to the wooden board. Besides endothermic reactions, they also observed exothermic reactions, like the infamous whoosh bottle. So the next step was to model the breaking of chemical bonds. Obviously, when you break bonds, you give the atoms a chance to form new bonds, and that can be modeled as well, in both cases using a ramp, a magnet, and a marble, and we also had access to a speedometer to keep track of the speed, the kinetic energy of the marbles in play. Next up, my students were able to play around with a computer simulation that involved object A trying to kick off the bond between object B and magnet 1, and then a new bond being formed between object B and magnet 2. The video linked above will actually show you my explanation of this exact simulation. I guess I'm going to have to do it again because my husband just walked down the stairs like an elephant. Let's try it again. The video linked above will show you much more detailed explanation of this exact simulation. So the simulation comes with this beautiful graph showing you the speed of all the different particles in the system. And when you plot that, you follow the kinetic energy, and then students have to make this pretty big leap to connect kinetic energy to potential energy. This is the one for the endothermic reaction. The video above details the endothermic process and how to model it exactly like this. The logical next step is to go from endothermic, with the beaker frozen to the wooden block, to an exothermic reaction, like the one shown in the whoosh bottle. Similar story. We're connecting the particles in this simulation, their kinetic energy, to the actual potential energy. Again, big leap for the students. Another video in which I explain exothermic reactions and how they can be modeled using the simulation. Key for students is repetition. So here are 4 additional reactions that really drive this lesson home. First one involves putting copper in the flame. You keep on putting it in the flame, definitely endothermic. It just otherwise won't want to react. Magnesium is a lot easier to combust. Take that little strip, put it in the butane flame, clearly exothermic because you don't even have to keep holding it in the flame. Again, more exposure to drive this lesson home. The decomposition of copper carbonate. Again, you need to continuously hold the copper carbonate into the butane flame for it to darken, for it to decompose. Last of these 4 reactions is the single replacement of zinc. You're not seeing that exact reaction here, instead the pop test, and again my student burning his hands almost by testing for the presence of hydrogen gas. So 2 of these reactions were endothermic, 2 of these reactions were exothermic. How can we model that? Breaking, making bonds, and how can we simulate that using a computer simulation? But I recently created a video on the 7 must-know chemical reactions. You want to know what the other 3 are? Check out the link in the description above. So all these lessons in this storyline finally drive home questions that students can form. And those questions, we put them down together on a so-called discussion board. Whether you do that printed on your blackboard, on a whiteboard, on a poster board, I'm showing you them here on a digital display, because by seeing these questions over the lessons throughout the year, it keeps them thinking about what may be happening in all these different chemical processes that they've been observing. And what you then would hope to happen as a teacher is that there's going to be some changes to these questions, some revisions, some added questions. And the ultimate goal, of course, is for students to come up and design a model. The model that I'm showing you here is for the exothermic reaction involving the combustion of magnesium. Relatively weak bonds are broken. I had to think about that one. They're broken now, which required some energy input, and much stronger bonds are formed as indicated by the larger blowtorch. Weak bonds broken, stronger bonds formed, exothermic. Energy release, hence all that light release. So putting the two graphs together, the kinetic energy from the computer simulation, the potential energy, nature favors low potential energy, kind of shows you the opposite. This is a really tough concept to crack, but one of my students came up with an ingenious idea to basically connect the two. Are you ready for it? How about that bicep curl? I gotta lift my arm. How about that bicep curl? So the left graph shows you an exothermic reaction, so very strong bonds are formed. The graph on the right shows you an endothermic reaction, and so strong bonds instead were broken. So if we bring in those bicep curl images, maybe that will help students understand the difference. Exothermic, strong bonds are formed, lots of energy release. Endothermic, strong bonds instead are broken, less energy release because it needed to be first absorbed to break those strong original reactant bonds. I'm briefly showing you here the traditional potential energy diagram as the reaction is progressing. I've put in the bicep images and I'm showing you the heat of the reaction, the original potential energy of the reactants versus the potential energy of the products, as well as the activation energy. The importance, however, is that students come up with their own model that's general, not specific necessarily to a given reaction that they've observed, so that they can basically draw conclusions for the various chemical or physical processes that they've been observing throughout the storyline. And that's what this diagram shows right here. In this particular case, weak bonds are broken, strong bonds are formed, hence the big bicep on the product side. But if we go in the opposite direction, right, we're now traveling from right to left, strong bonds are broken, weak bonds are formed, hence this is an endothermic reaction. Again, a general model that allows students to understand the big picture of this entire storyline. And then the key thing as a teacher is to bring it back to that discussion board. Are there some questions that we've now satisfyingly answered? Are there new questions? Are there questions that we need to revise? And this is kind of what we ended up with at the end of the storyline. And what is the message that we want our students to take? So you're seeing here a little clip art of a Google Keep icon. So check the video linked above on how we can encourage our high school students to take notes in Google Keep, and possibly also to make notes, how to process the notes that they've taken for further learning. My wish for you is that this video may have convinced you to implement this storyline into your curriculum this upcoming school year. I would like to say check out the video linked above, but I might have reached my max of video links. I think YouTube only allows you about 5. But in any case, the featured video on my YouTube channel is the first 7 lessons summarized. Check them out. You want to join my journey? I hope you do. Join this storyline by going to the description below and clicking on the link to my landing page that gets you all these documents, all these lesson files with the associated keys. Don't forget, these are all connected to the Next Generation Science Standards and the New York State Science Learning Standards, HSPS1, Matter and its Interactions. These are three-dimensional lessons focusing on student inquiry. For those of you that have been watching my videos, you know that I always end with the same Dutch sentence. So I'm going to expand your Dutch vocabulary now. What is storyline in het Nederlands, in Dutch? A storyline is een verhaallijn. Verhaal, story, lijn, line. So a storyline is not just some hodgepodge of cool labs that we throw at our students. It's basically a connected rode draad, red thread that connects all these labs together. Verhaallijn, de rode draad. Thank you for watching, bedankt voor het kijken, and see you in the next video. Tot ziens!